The real trick here is whether the thing will work or not. Yeah, can you hear me? Yes, you can. Good. Okay, I've got a huge cornucopia of slides. I've dug back in my library, and so I've got a huge number of slides, and I'm going to run through them very, very quickly. I thought two things around which one should think about this is business. You've got an attitude, obviously, of collaboration, but also competition. So, we compete with Allies Morrison, but also we collaborate with people. And it's important to think about that. Innovation is another thing that's really important to think about. Is what you're thinking about actually just an evolution of an idea, or is it a revolution? It's something that's really radically going to change everything. So, of course, I do this occasional thing of doing shows. So this is the one that Gensler saw my presentation a while back, and they built that building. Ours building doesn't get built, but the important bit here was that we were using interesting tools in order to develop the geometry. Tools which then we decided were worth pursuing with other people. So I think, Jay, is he here? No, I'm not sure. So we formed the Smart Geometry Group. So 2004 was one of our first events. And that was about collaborating with lots of people to develop tools for this new world of interesting and complicated geometry, and of course, CAD management and that kind of stuff. I'm also co-chair of this event that happens in September, so I think you should all come to Gothenburg and participate in this event. We got, I think, 17 workshops to choose from before the event itself, and the event is two-day conference, so I hope you will look it up. So these are the kind of tools that were being developed at the beginning of the smart geometry thing, which is the GC, generative components, and all the kind of issues about having folding, unfolding panels and all those kind of things. And you think, well, do you develop your own in-house technology to do this stuff? Or do you actually collaborate with other people to make sure that it happens out there? Of course, when you do that, you will find that actually collaborating is a good idea. This is the Crick Institute, so that was designed parametrically, the roof. Whenever the mechanical engineers came along and changed something, you change the parameter, you change the shape, you spit out all the drawings, and that is some of the models of the 3D roof. And they all look identical, don't they? But they're not identical. Everyone is marginally different from the other. So when you start talking in more general terms, this is something I was presenting at Chalmers. So I had 5 points to bring up. It's important to think about materials, and wood, of course, in Sweden is a very important material, and it does have lots of interesting aspects, and we'll talk a bit more about what we can actually do with wood. Clearly, we need to change. We, as a society, CO2, climate warming, it's a real problem, and you can see where the fat lives. And I'm afraid the fat is going to have to start to thin down a bit. Whereas the thin parts of the world are going to be expanding. So structural research is another area which is obviously very interesting. So timber tower is something that we developed fairly recently. Of course, they've got interesting aspects about how buildings behave and all the rest of it. Everybody loves shells, and shells are great, and everybody does very innovative things. My problem with shells, though, is, hey, it's only really solving one-story buildings. And actually, most of the time, we're talking high-rises. I think this is an area where I think new technology really will come to the fore, which is integration of services within buildings and rethinking entirely how services work and what they are and what they're for. So this is an area where, if anybody has an interest in this, it'd be very good to talk to them. And things like electric wiring, completely crazy system. Why do we have electric wiring the way we do? Now, most innovation doesn't start within architecture. It starts in other places. So, of course, the car industry, all these other industries will have innovations that we'll want to use. And I think most critically, the robots are coming. And so things like robotic assembly of buildings and the like is clearly going to come along down the track in your area. And I think basically when you talk about robots, you want to be on their side. Don't fight against them. Bend them to your will. Get them to work for you. That's what robots are for. So computational design is, of course, another thing. Is, you can compute millions, if not billions, of alternatives, and how do you evaluate which is the best one, and that kind of stuff. So this is some of our Skypod stuff. Now, why do we actually innovate? And I think this is where I think you really need to start thinking carefully about what you're doing. Is things just don't work the way we want them to. I don't want to hang around and wait in a station for a train. I want things now, on demand. This is what the modern world is about. And we have got huge problems. This is from Bill Mitchell, who sadly died a couple of years back. He was at MIT, and I've been inspired a lot by his work. Urban transport is one of the absolutely critical issues about how we're going to behave in the future. And you can see all the kind of issues that arise with the transport systems as we have. And, how do we actually change radically the way we think about transportation is one of my things that I bang on about. So, for instance, you get Corbusier. Corbusier said, look, this is the future. It's going to be wonderful. We're just going to love it. But that's actually what we got. And this is what we built. And if you think this is a good environment, I think you should leave this room now. So, why are cities so large? What's the whole point of having big cities? Well, it's a mathematical issue, and it's very, very simple. The size of any set of people, the connections between them goes up as is exponential. So big cities, you have hugely more choices about who's your partner, who do you work for, or do you specialize in something or other. If you live in a small city, you might only find one employer. If you live in a big city, you can work for PLP, or you can work for Allies Morrison, or you can work for Foster's. Come on, this is why cities are big. And there is no real limit to that, because the bigger you get, the more opportunities there are. And therefore, big cities are going to go on growing and will probably take over the world. So then, of course, we have got this other downside. And I believe that tomorrow we have a gentleman landing. Actually, he landed this afternoon, who doesn't believe this. And I think he's wrong. And actually, if any of you feel like assembling tomorrow outside here and marching down to Trafalgar Square, please do. We do definitely, as architects, we have a responsibility to deal with a lot of these issues. So technology, this is one of the kind of issues that are weird. Traffic technology develops so slowly. It's ridiculous. 20 years, 25 years, and then it takes 160 years to get to high-speed trains, whereas we built the motorways in 65 years. So suddenly you think, hang on a moment, did we suddenly choose something different a while back? And the answer is yes, of course we did. And one of the things we chose is actually basically crowds. Crowds means that you have individual control over what you do. And you don't have these huge objects that take over everything. And my bet in the future is flexibility will win. Flexibility is what everybody's looking for. I want it when I want it, here on command. So obviously it'll be available, whatever you do will be available from something like a smartphone. So these are some of the slides about that I picked up from the past, and that's the Abu Dhabi airport that my team did the geometry for. And these are, of course, the various areas that you have to think about carefully when you do these things. So what kind of technologies are you going to have? Well, you've got geometry, CAD, well, that's already there. Everybody's doing that. Visualization and rendering, everybody's doing that. This slide was prepared back in about 2000. Parametric design, that's now widely available. Pretty well everybody's got it. Simulation, yes, everybody's pretty well doing that. So the synthesis is, of course, how you think about design and what you think about it. We need to think about materials, environmental systems, movement systems, movement in society, aesthetics, and communication, how we civilize that. And of course, you need to develop a thought process about how you investigate and how you work with various people, and what are the kind of things that you need to pick up and do in order to do these things. And of course, you need to have various networks things, and these are people that I've been worked with. This while I was at KPF, But obviously, there are lots and lots and lots and lots of people that you need to work with and you will want to work with. Oh yes, there's Jay. Is Jay turned up? Yeah, there's Jay. Jay is at the back. Okay. So he was one of the creators of the smart geometry. The thing on the left is the Abu Dhabi airport. It's got the biggest glass wall in the world. So the client said, is it the biggest? And we said, don't know. Do you want it to be the biggest? And we said, yes. So he said, make it so. Come on, let's go next. Okay, yeah. So CO2, obviously, this is the real problem. If we carry on business as usual, this is what is going to happen. But maybe, if we have next slide, we can do something like that. We can change the trajectory in which we go. Okay, so one of the interesting things about timber is, of course, it's ecologically very good, but the one and big issue with it is drying the damn stuff. So if any one of you got a really good idea about how you dry out timber, please tell me and we can do something about it. Okay, so strength to weight and stiffness to weight. It's surprisingly strong wood, it really is. So when you start looking at the structural material, you can begin to think about competing it with other materials like steel and concrete. So 40% less waste because you can recycle the stuff. And this is an interesting one, is weight. When you build something in central London, the weight of the building matters a lot because you've got to put it on a lorry to bring it here. Also, of course, you've got to build a foundation, and the foundation is proportionate to the weight of the building. So lighter buildings make a lot of sense, and it's quicker to build as a result of that. So this is our Oakwood Tower. Some slides of that. That's Kevin Flanagan, one of the partners who has been developing that, and this is another development in a place I can't tell you, for a client I can't tell you. This is Deloitte's headquarters in Amsterdam, which is the most sustainable office building in the world. So it creates all its own energy. It's got photosynthetic cells on the other side. This is the atrium, which actually people love. They adore it. It's north-facing, which is one of the big issues, and it changes, of course, its character with the light. And of course, this is a very intelligent building. Some of our competitors set up a lab the other day, and they said, it's terrible, most buildings only have one sensor. This building already has 12,000 sensors. Every single light fitting has got a sensor in it. And so it talks to each other, and the building knows about things like how it's going to be occupied. So if, for instance, one day it's not going to be very occupied, it closes down the floor and doesn't use it. The building itself knows this, or the AI bar behind the building. So, of course, it will also know about your preference for heating and cooling and so on, and it will carry that preference along with you, depending on where you happen to be wanting to go. And you, of course, connect to the context, which is all the services that you require outside the building. What you're about to see is not science fiction, it's science future. We have an urge to build ever taller buildings. Partly this is economics, and partly an expression of human spirit and aspirations. Tall buildings use less land and are the core of any successful city. Their shapes define the skyline and the signature of the city. So what limits our ambitions when it comes to the shape? The critical design issue is how lifts function. Today, they simply go up and down vertically in shafts. This topology is unlike any other transport system. All other systems have multiple vehicles in one-way track. This is by far the most efficient way of organizing transportation. By redesigning the track to be similar to a funfair ride, we suddenly have the opportunity to have complex paths for a novel lift system, the Skypod. Unlike a funfair ride, we want a smooth, stable platform. In practical terms, this means a pod which can rotate in two planes so that the floor is always horizontal, although it can tilt to achieve a comfortable ride, such as when traveling around corners or accelerating. The critical issue is how the pod is entered. We have settled on having 3 potential axes, 1 through the back and 2 on the longitudinal axis. These are there to allow different types of stops. We have designed a propulsion system with linear magnetic propulsion. Our calculations show we can build this system to lift 4.8 tons. Normally, we would expect no more than 25 people giving each person a generous half square meter. The two entrance configurations are used in different cases. At stations with large volume where people and cars need to enter quickly, we use the exit entrances on the long axis with platform axis. These platforms can take high volume of passengers, but are also sized such that cars can be driven into the skypod and delivered directly to the right floor. Higher up, where the track is vertical or near vertical, we can access the skypod through the rear entrance. The size of this entrance determines the track width. We have deliberately designed the system so that there is an opportunity for spectacular rides. As you ride up, the city unfolds. At the top, there is the opportunity for a circular ride to experience completely extraordinary views. Some of the skypods will be used for sightseeing. The track can travel around corners and change plane and will incorporate switches for more complex networks. Suddenly, huge new design opportunities open up. We are no longer tied to the idea of a central core, but can be free of those constraints. One opportunity is to relocate the main structure to the outside of the building where it does most good. Alternative shapes of buildings are suddenly possible, from extreme forms of topologically complex forms to alternative visions of what high-rise living could be about. Technology drives innovation. We expect this to be true in vertical transportation as in all other fields. Roll on the future. Let's have the next slide then. I think it's come up. Right, so this is one imagination about the kind of forms that you can begin to develop. I'm not saying we're necessarily going to do this, but the point about it is we've been so constrained by lift technology, we haven't dared to think about really interesting shapes. Right, so here's another interesting shape. Kilometre-high building. Incidentally, that kilometre-high building, you will find it in the Royal Academy in the exhibition. There's a model of it there. And so this is how the technology could conceivably work. So it's a track system, and of course it's got switches. I'm quite proud of the switches because they have no mechanical moving parts. It's all done magnetically. So this is the kind of thing I think. So of course, what's really important is you have got to be able to have torsion, because torsion is the only thing that allows you to change plane. And this is a typical slide. And this is a typical slide. And this is a typical slide. And now welcome to the future. Today, streets are dangerous places. Our children can't play there. Cars are far too dangerous. But maybe we can change all that. Autonomous cars are coming. They'll be so much safer. They will refuse to run over a child that strays into its path. And they will need far less space. You can put that space to good use. Playgrounds, trees, cycle paths. Finally, the street will again become the heart of the community. Well, how will this reality come to be? Meet the car tube, a new mode of urban mobility that fuses two technologies, mass transport and automated cars. Car tube works a bit like the internet. Its roads are the optic fibers, their intersections are the switches, and the cars are the information packets. This means direct travel without interchanging. The stop-start model of current transportation is replaced with a fluid, integrated network. In our cities, car tubes roads would operate like the segregated tracks of railways and motorways and can be either above or below ground. The most efficient layout would be a simple grid. Here we show the intersections of the below-ground system. The main tunnels have two parallel lanes, much narrower than a normal road, because the car's digital trains are robotically controlled, and of course electric. At the junction, the meshing of the cars is achieved by stretching the spaces between vehicles to allow them to get into the right lane for the next intersection. The result is a system that never slows down or stops.
Since no off-the-shelf traffic simulation software gave us the chance to reflect real problems and potentials of the car tube system, we had to develop our own. So this system we have developed takes real-life data with modifiable parameters and helped us to see some important indicators such as how many vehicles needed in the system, what is the average response time or average speed in the system, what are the points of density or congestion. We making a single global system working with many autonomous agents, namely cars, so that its capacity to react to a problem or a change in the overall network is very high. Because it's looking at multiple indicators all the time and analyzing them as a whole. So this gives us at the end a very efficient and very adaptive network.
Of course, all transport systems, either trains or cars, will always have idle vehicles. These vehicles can simply loiter within the system or park themselves in purpose-built stacks close to their destination. In addition, vehicles could also take advantage of underused infrastructure or buildings such as grade parking or multi-story car parks. Naturally, as demand increases, so various forms of stacking will evolve. Cities grow, and sometimes they outgrow their initial infrastructure. What is needed is a system that can grow organically and fuse with existing infrastructure. CarTube, as a decentralized and underground system, will seamlessly expand as the city grows. In today's city, infrastructure is often a barrier. Districts are separated by motorways and railways. By putting CarTube underground, we free up land for people and parks, and the city fabric will be made whole again. But cities are three-dimensional. CarTube will not only connect horizontally, but also vertically, making possible a new form of seamless horizontal and vertical transportation. Within the CarTube protocol, vehicles could flow directly from below ground to the top floors of ultra-high buildings. With no more cross-modal waiting, no more sardining in the underground, no more timetables, and no more worrying about parking, CarTube is the next best thing to teleportation.
I've got a few more slides about the CarTube, but we might take a pause because I'm now coming up to my 40 minutes. But maybe we can have one slide more, just see where we are. Oh, right, yes. So this is the basic idea. The cars can turn into trains, and what happens then? Next. I'll just take a few more seconds to do this. And this is the point. We've already chosen. Almost all transport takes place on roads already. We, as a society, have already chosen. But we've chosen a system that is polluting and dangerous. And I think we need to change that. So I think I'm going to stop at that point, and we can talk about other things later on. Okay, thanks.